Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our practical lecture 1.1 about C programming and understanding the concept of scheduling, which is really an important factor in HPC. This is just an introductory lecture, so we can't cover, of course, all the magic of C programming, and also from the scheduling perspective on HPC systems, this is a huge topic. But we try to understand really why basically scheduling is an important factor in system software, how it is connected to monitoring. And then basically we will use a small C program, hello world, so to speak, that we first, as a normal C program, will execute on the HPC system and compile there and so on. But also we'll try to understand elements like login node versus compute nodes and so on our teaching infrastructure. But before we go into the material of this lecture, let us review what we had the last time. And the last time we had lecture 1, which was basically the 10,000 feet perspective on high performance computing in this course. So we motivated high performance computing. We connected it to supercomputers. What exactly is a supercomputer? But we also had lots of terminologies and HPC basics, as I would like to call them. If you remember, one of the basics is obviously our heartbeat CPU, right? Heartbeat in the sense that it has a certain frequency we learned. And when we think about the multi-core processors we have today, they usually have a very high single thread performance. And they're really the number crunches we still need in a computer. And this is one of the building blocks, obviously, the processor, right? On these processors, there will be processes running, which I indicated here with P1, P2, P3. Especially if you want to have then an HPC system, we learned there are different node cards, there are different racks, having many of these multi-core processors really then in a very tightly integrated manner in such a system. And then we went a little bit further. We said, okay, when we have all these processes, this is not parallel programming. They run individually, they do their own executions. This would be not a magic of using this high performance computers potentially. So what can we do to make them work together in a cooperative way? So to do this, we basically need a certain architecture part, which is this distributed memory architecture. If you remember that a processor has certain cache levels and a memory that is basically not accessible from any other processor, right? Especially if you come up to a large system like this here, you basically cannot just, like in shared memory, access, load, and write to the memory. Hence, you have to send messages, which we motivated with a so-called message passing interface usage, MPI. And we will have a little bit of an impact of MPI today as well. But of course, the next lectures, lecture 2 is MPI, lecture 3, 4 will basically then connect to it and provide much more details. Important is to understand that these processors run all in parallel with processes. And the beauty of parallel programming to leverage really high performance computing is to use all of these processors and its processes running there in a cooperative way. And you can basically do this by sending, receiving messages. You will basically have some data that you get from one process to the other for certain reasons, usually for scientific applications that we will talk in the course. We also learned that there's this shared memory concept still existing, especially when you think about within the node, right? Often we say within the node, we do shared memory programming, and across nodes, we do this distributed memory programming, hence MPI across the nodes. And when we come now inside a node, we have still this processes with different level of caches here. And we have a direct access from all of these processors to the memory. In other words, you see that on the right-hand side here, we call that threads that can access a shared memory space, let it be writing and reading a variable. We have also learned there is a so-called NUMA and CC NUMA with a cache coherency link. So where it is basically a distributed memory, you see that a little bit here, but there's a cache coherency link basically enabling us as programmers to just see it as a shared memory system. So we can still as human, let's say, access to memory. Obviously, there are certain parallel regions that need to be specially protected. You have race conditions around the variables that you have to protect. Hence, we will have a complete lecture on the OpenMP standard, which is really the de facto standard doing shared memory programming in the HPC arena. And these are very important terminologies we looked in. Multi-core processor, you should know. Distributed memory architectures, you should know. MPI should be, as well as OpenMP, be something that you really understand. Also, the major difference between shared memory and distributed memory. We continued further with the HPC ecosystem technologies, which put it a bit bigger in scope because we had the basic architecture with the multi-core processor. And we heard about the problem today that we basically cannot increase the number of these cores on this multi-core processors to infinity, mostly because they're running at a very high frequency, creating lots of heats. And if it's let's say, lots of heat on one chip, it disturbs basically also the chip so that it will not gonna work. Hence, the idea was with GPUs and so-called accelerators today to create still lots of processors on one chip. That's done in the hundreds and thousands these days. But the point is that these basically have just a moderate single thread performance, a moderate frequency. So in other words, they're not getting so hot. And this enables us to have significant throughput in a GPU. And that's why today you find many applications like here, the earthquake simulation that we had, which is a bit appropriate to think about in this course here in Iceland, thinking also what happened in Grindavik and so on right recently. But this is something which is now used in parallel computing a lot. We also learned in the last course that usually to fuel the GPU with data and to basically use it, it always needs a host CPU attached to it. So the GPUs cannot run alone in space. Usually you have to load the data from a CPU to main memory, then into the device memory in order to process data there as a GPU. We basically reviewed very quickly deep learning, although there will be a complete lecture around it. But we learned that deep learning is fueled by GPUs. And this is not only the case from the Tesla or NVIDIA series, this is also nowadays with different other accelerators from AMD here, the Instinct cards that we, for instance, find in LUMI, in the supercomputing infrastructure provided by the EuroHPC joint undertaking. But coming back to deep learning, we learned that GPUs are a key, okay, but why? The reason is in the learning process and how the learning algorithms work, which are mostly coming back to matrix-matrix multiplications, matrix-vector multiplications, something that we illustrated a little bit here with the color code. And the color code is now the key essential point, because you see the mathematical rule how you would compute a matrix vector multiplication is exactly in these colors. And it shows nicely a kind of independent computing, right? In order to get the results of A here, which might be, the result we're looking for of this particular part, you just essentially need these specific colors independently from the others to compute. Hence, you can break down this big matrix if you have maybe, of course, this is a toy example here with 4x4. If you have a large matrix built on these tensors that you would have here in the deep learning, CNN example, then you can break this down into smaller pieces, and it's exactly what the GPU is doing, computing these really independently. And it's very simple operations. If you think about just a multiplication, of course, the whole matrix with vector is very large and would be, let's say, taking lots of time. But having so many processes to do the simple operation enables us to have a significant throughput of this deep learning. And this is what materializes in lecture 7 when we really talk about deep learning, and then also going further with Reza's part in CFD, where more and more codes are also ported to GPUs. Then, if you think about where HPC is also useful in that context, was not only to make a speed up of learning. So speed up refers to the training that I need for deep learning to learn from a particular type of big data, let's say weather prediction. This learning has several parameters. And we see that here a little bit what we call partly also hyperparameters, like the batch size. What is the optimizer we're going to use? What is the learning rate? These are all not obvious to you. We will review them in lecture 7. This just should motivate that often the accuracy or the error rate, if you want, of a deep learning network in a real application is often determined by choosing the right hyperparameter. So it really depends how you choose these particular elements to get specific performances out of it. And this refers to something we also call partly neural architecture search and hyperparameter optimization, where HPC is another big value on top of not only, let's say, speed up the training, but also making better models, because we have the opportunity to really optimize these hyperparameters. And this can be used in many applications. You have here one that we basically had last time about basically image compression techniques and so on, another idea how to use deep learning and elements like that. Just finally, because also students came to me after the lecture and we had quite a nice chat around 15 minutes about quantum computing. So what you can do there, what we do there. We had, let's say, just one slide there. And I had you pointed to a YouTube lecture where I introduced a quantum annealing, at least with D-Wave, which is just one form really of quantum computing. We also said that there are different EuroHPC JU systems which are currently basically procured and will be made available to the European researchers, which are built on different technologies. So D-Wave is just one example where my team is doing lots of publications with. But of course, stay tuned, the future is coming, that quantum computing is in front of our doors. It's not something which will come in 20, 30, 40 years, which some people say. We really use quantum computers right now. And I think the takeaway message, I think, in the moment to really think about real applications, consider them as another type of accelerator, right? That's how I see it in the moment. GPUs is one type of accelerator, very good for deep learning and so on for learning. Quantum computing might be just another interesting type of accelerator right now. Thinking back about the modular supercomputing concept, right? One modular element could be the quantum computer part, which then, for instance, can do optimization in an extremely fast pace. Because we want to do a quantum computing course at some point in time at the university, this course does not talk very much more about this. But of course, there's also a final project around that if you're really interested, especially those students that approached me after the course. But let's just come also to the idea of today. And how today is a good example, what I wrote in the beginning when I showed you the outline. So we'll every now and then, these lectures have some additional, let's say, lectures, practical lectures, where you will then also get some information which is directly related to your assignment or that you can also use for your final projects. So today, the idea is really understanding a little bit about compiling, programming C programs. And that's not to be a big C programmer. It's rather to give us an environment and, let's say, a very simple application in a way to understand two things. Firstly, that you need modules, HPC system modules, which is an important concept in HPC, as I was alluding last time. But then also the idea that executing these programs, even if it's simple programs, should be done in specific ways. Hence, the first course part will talk about how we basically write our first C program. I will demonstrate this. I will basically do this in our Alias system. We will compile it and load the right modules. But we'll also quickly learn that executing C programs, just as you basically would do on a laptop in the directory, execute, let's say, double click on the executable, would be not the preferred way on a HPC system, because usually we are in something we call a login node. The login node is not obvious to you. We will see how that materializes throughout this particular lecture, and this is one of the learning benefits of it. Hence, this is not a good practice, and I will motivate it then. What is a good practice? What is basically referred to scheduling. Because you have a multi-user environment, we touched on that a little bit the last time in the last lecture. But basically, because you have multi-user systems that actually are concurrently used by many, many users, could be in big systems up to hundreds of users at the same time, we need a specific software here, for instance, Slurm, that is part of the HPC system software to really manage all of these users, to understand what jobs or tasks, what we want to run on these computers are running, how long they are running, when could the next job be running, and so on. I will demonstrate this also in a very simple fashion. Hence, we will use the C program a little bit also as a tool, so to speak, to show you the idea of how we use the HPC system earlier with a teaching partition U-turn. And this is now an important part again, to understand that one HPC system often has different partitions. Even if you have, let's say, so and so many CPUs inside, there are certain subparts of the system which are then partitions, and I will make the case for it. And if some of you know, in a couple of years, we had the U-turn cluster, which was a dedicated piece. Now, basically, we have a new U-turn. It's not the same that you used to have in the couple of years before. For those students that know it, that is really a new teaching partition only on basically the HPC system earlier, referring to compute 1 to compute 4 nodes. And I will show you this. By doing this in a, let's say, right way, we will use a scheduler then to execute the C program on this compute nodes. Just again, a point that this is not the full lecture for C programming. Obviously, there's many more things to C programming. It's much more the helper tool that we need to understand scheduling better. So the learning outcomes are then really how to create and use high performance clusters, especially understanding partitions, lock-in nodes versus compute nodes. In a way, also the accelerated nodes we will shortly look in with GPUs attached, so to speak. But also very important today would be the HPC environment again, the tools, so C compilers, what are the modules to have, let's say, an MPI implementation. So the message input passing interface is something we're going to use in the next couple of lectures. So we will start with a C program and extending this C program in the next couple of lectures with MPI. But in order to do this in the right way, we already want to see what MPI version we can use. And there's a version called OpenMPI, for instance, that we can use. And this would be one of the learning experiences as well. So let's start with the first part, really, as a practical part, just motivating C a little bit. For those of you who are here in the university, I know Java plays a big role, and C sort of like Fortran gets more and more forgotten. Many of the scientific applications, however, that you have today are written in C or C++, and actually many of them are still also written in Fortran. Right, the Part1 programming language, especially those which know, NWP, numerical weather prediction, weather forecast, system sciences, still have lots of codes in Fortran. It would be very hard to port them easily because they have been peer-reviewed, based on publications, based on data validation techniques over decades now, and just redoing them in a different programming language like maybe Python would take a long way. Also, Java is an interpreter language, as some of you know, so it tends to be a bit slower, right? So compared with C binaries and so on. Hence, you see here one hydrology parallel application, understanding the flow in terrestrial systems, which you have to have then again, for instance, in these different codes, which are actually simultaneously coupled and run on a supercomputer, which is the, let's say, groundwater modeling. Then you have the land surface model helping there, and the atmospheric level, Cosmo, CLM, and Pathflow, all connected with an Oasis coupler. And this is all in C. Other examples are the NEST simulator here, simulating, if you want, the human brain with, let's say, a spiking neural network model and approach. So this simulation kernels, again, are in C++. So C has its role, and you will see coming to the lectures 9 to 15, which are then more on the application level, C and C++ codes. In fact, also Fortran codes are still used in CFD as well, in computational fluid dynamics, and in many other scientific applications. However, don't worry, in this course, you don't have to be the perfect C programmer. It is also true that many of these scientific applications are often reused by scientists. Even they don't know the real C programming behind them. They reuse the code, they run the code in HPC, and do their research on the configurations, on the different data sets, and so on. So also here, this course has not ambition to make you a perfect C programmer. It's just more a vehicle to understand the concepts of the course, especially power programming, scheduling, and the architecture of HPC systems. Coming to this, the architecture, we have learned a little bit about this from the practical lecture 01, if you remember. I said there's a nice documentation from our National Competence Center from the team at UTS, where you can actually see what the Allia cluster entails. And you would see the hardware specifications include several compute nodes and with different type of CPUs. You see here Intel CPUs, there's standard compute nodes, and all of them are basically a little bit, let's say, as a sub management criteria in the hardware, accessible via certain partitions. You see here, for instance, the partition names that you can use in so-called job scripts to really address, and they will have their dedicated features. So one of it is here a high memory partition, showing that the memory, especially here in these, is quite large, right? Compared to other nodes, maybe where the memory is just not so large. Just one example. The other concept you see when you go to this documentation is a login node, right? The login node will be a central part of discussion today, where you basically ending up when you do your SSH connection that you learned in practical lecture 01, you logged into it, and then you're suddenly in your home directory on the machine on a so-called login node. The login node is something which is a helper tool for the HPC system in one respect. So you're not supposed to run on the login nodes very computation intensive tasks. The idea is really to use the standard compute nodes that you have here on the left-hand side, right? So this is important. Or if you have codes running GPUs, they should be running obviously on those nodes in the big HPC machine here, which are equipped with the GPUs. So the login node then needs to have a mechanism in place to basically shift the code, distribute the code to these compute nodes. And that is exactly what scheduling and the MPI environment later and so on entails. And we will establish now step by step so that you really don't need to know anything about this. This is exactly what we want to motivate today. And we start in practice again where we left in the last practical lecture. If you remember, I recommended MobiX term. I already logged in here for the time. So we used our, SSH key pair. Just come back to the slide because maybe that's important just to repeat once again. You have your SSH key pair. If you remember the private public key, I already, and you will in the course, share the public key with the administrators of the Allia system. They will provide it at the system level, but you always keep your private key pair. Right, then once you establish an SSH connection, you will use a private key pair to show that you have the matching one to your public key and are allowed to actually connect to the system. Hence, you need basically 3 ingredients to basically connect to the HPC system with SSH. You need the host name here, allia.how.is. You need the specific username, which is in my case Morris, and remember that also varies from machine to machine. And then you use a private key. This will be part of the first assignment, so you also will have your hands on that, especially also how to create them as SSH keygen, for instance, also with puttygen for those that are in Windows. Hence, here it's not about the creating the key. We are logging in, we're using that information, and then we have the welcome screen, as it is called here left, that we also have here in the real demo. So another idea is here to see, especially in the context of the login node today, as we discussed. Now I'm really Morris at login ear HPC, right? So I'm on this login node that I just presented on the slide. And that means, I am on Utun, but I'm only on a very interesting small fraction of it, right? And this fraction is now where we do a lot of work, but not the computation intensive task. Here you would do other things, right? Like our Unix command we have learned in the last time. We browse through directories. You see here, I already basically created an MPI and a couple of other directories for the course hours today. We have still our funny Morris file that we had in the first practical lecture, right? That is maybe also time to remove because it was just a test. But in the end, we have here another directory created. And remember, you can do this with mkdir. But of course, I already created this here. So we will see there's already a directory called hello, which is quite important for us. So, and when we now go to this, directory, we see a couple of files. And as I said, now the idea is to think about how we can create our first hello C file. But we also learned we need to want to use this kind of scheduling. That is something in the second part, which we're going to use. So we firstly focus here on hello C. What is this? And of course, I provided this already for you. So let's look into it. It does nothing else like basically including the standard IO header and then print out hello world. And that's it, right? Return 0 refers to the point that this executable or the C program was actually computed in a correct manner. So there were no errors. So this is just a simple text file if you want, right? So, and obviously that is not really a C program, it's just a text file. And just that you know, of course, the same elements I have already documented here in the slides. So we go in parallel a little bit with the slides. I would recommend to create the folder as I was doing on earlier. Once you have access, the HPC course folder, create really an MPI folder and an hello folder, and then put this in, because we will have more MPI codes later, which maybe could be put in a broadcast folder and etc., or collectives folder. So these are things we learn in the MPI lecture, but this is all based on the basics that we learned today. Hence, we have these two ones. We looked into it, and the C program usually needs something we call a C compiler, right? And it's part of the HPC system module environment that you already know from the last time. So the idea of what we could do, if you remember, was to now think about that we are on the system. I will increase the font size a bit. We had this interesting idea of module avail, right? Which gives us all the different software and scientific software elements which are on the system. I don't have the time to talk to all of them. We will actually face here and there some of them in the course, and some of them are important to us today. Like here, for instance, you see an MPI implementation based on OpenMPI version 4, exactly the 4.1.4.1.2. This gives us then the environment we need to compile later, also in lecture 2 and the practical lecture 2.1, to really use the MPI elements, because important today is to understand that we will not really write an MPI program today, right? It's a C program only. We not make use of MPI because it would be too much to put all in one lecture. But we also learned in the last time we can investigate those modules more. And again, I actually here in MobaX term had basically marked this, and then with the right click on the mouse, I can just copy paste it. It's maybe good for you as a short hint. And it gives us some certain information. In some cases, we have to load something else, like for instance, a certain version of GNU, or let's say another dependency as it is called. Here, we are very lucky. We say this module can be loaded directly. Hence, we can just use module load MPI in order to, load this environment. So then let's look at this and see how we use this. We remove here the hello executable, which was just one of my tests, but we'll also now come to the idea like it's recommended here. We just use this environment to module load it. And now I have already basically established the way how I can, have access to the C compiler, but also one that understands the MPI, because it's an MPI implementation. Hence, we use something called MPI-CC. And this is, of course, all also documented here, here in the different ones. And we will use this again in lecture 2, practical lecture 2.1. So this will become quite more often used. And here's another example of a C program and C++ program. It's a high HPC clustering algorithm, for instance, also machine learning, and basically something which is used really in application. Another good example that not only scientific physical implementations like numerical libraries or numerical methods based on known physical laws like weather forecast and all of that, is basically using C. Yes, also artificial intelligence still has codes which are using MPI, which are using C, like this HPDB scan. Hence, you see also the module spider here, and the idea that we're now using this hello C with a certain C compiler to get basically then a hello executable. That's what we want in the end. And we see here the module load MPI that I already did in practice. And what we want to do is now to compile it really to see if we have a valid code, which means we need this C code, MPI-CC hello C. This is a bit optional. I always want to have -O and have proper naming of this output, saying it should be just called hello. We removed it before, but now you see, hopefully, exactly it's there again. And you can also manage directly to see there's some certain difference in the writes here. So we didn't talk about in Unix and the file system so much about it. So these are read and write access on different levels. But here it's important that it's an X, meaning it's an executable. So we can actually run that. It's now a binary. So if you do, let's say, something like this, more means usually you can look into a file like more hello C. You will see that's possible because it's a text file. But more hello is not possible because it's now a C compiled binary, right? So it's not a text file anymore. The benefit is that the computer understands it directly, so we can execute it. And with this, would have something like, a real C code we can now use. Once again, it's important to understand that although we used MPI-CC, we used moduload MPI, OpenMPI, this is not really an MPI program, right? So this will be added in lecture 2. But before we do this, we need to learn the basics of scheduling and how to use a HPC system with executing. Because MPI will enable us to then use, for instance, 4 or 3, different nodes, maybe different cores on these nodes. And in order to understand that, we need to understand first what is a login node, what is a compute nodes, how I can actually manage with a scheduler to activate the compute nodes. Because once again, also, all I did in the practical here, which was a simple practical, obviously, is still basically here in the login node, right? So I never used really the compute node that we had in the system. And this is an important takeaway message. For that, I also want to go in a certain monitoring system in a moment. I will not explain it very deeply, just to say that now we have this hello code. So in theory, what others would know from your maybe other courses or so is, let's just execute it, right? So we can say in this directory, we have an executable, execute it. And it says hello world, fantastic. And that's the way basically how a C program is executed, but not on a HPC system, right? It works because obviously we have a fully fledged login node and it works, but you will see and notice that in HPC, we do it differently. And hence the way how you use a login node is more or less as a helper node. You can here and there compile if it don't takes long. You can work, shift, and maybe even here and there pre-process a little bit of a data. But if it's large computing jobs, everything which is really computation intensive, as we call it, needs to run on the compute nodes, right? So let's review that concept again when we now think about this. It's also documented here on the slides. And this is really the way not to do it, right? So remember that. It's not good practice to execute an executable on the login node. Here, the hello world, nobody will kill you if you do that. That's a very trivial teaching example. But the way it is used on the LEN login node, that's not what we want. What we want rather is to activate all of these compute nodes that you have read in the hardware specification of LEN, right? So we use the login node, that's fine, but just for preparation. And now we need something to activate this so-called scheduler. In one way, you can see it is sitting between the login and the compute nodes of LEN, right? We can use from the login the scheduler to activate and to use all of these different compute nodes, the different partitions we have here in a certain fashion. And this is something which we will establish also as a second part, basically, of the lecture today. Again, you would think, what a kind of big work, right? Why we should do this? Firstly, think about that this is a toy example. Think now about a climate simulation that would run for 24 hours, potentially only on the login node. So firstly, it may be running out of memory quickly, but also having not the processing power doing that in parallel. So there are many reasons why the login node is really, as the name suggests, your point of landing. If you log in, that's what you were faced with. And from there, we use a kind of Slurm scheduler or others on other HPC systems to really use the HPC correctly. And that will be part of the second part of the course. Just want to come back also to the documentation a little bit, that we have here the idea how basically the partitions are also in our documentation from basically the LES system. You see here the different partitions that are available. We will have a very specific partition called UTUN for teaching matters, but those that maybe are PhDs and already use ELIA, chances are they're using the different partitions here already. Also, what I basically then said with software, right? Your software, available software environments, module avail, and these commands, you see there are lots of different elements. You can unload modules, you can, have certain environments prepared for you. This is maybe something which those of you that are interested can look at. We will focus on the very few elements that are required to go towards something we call MPI later. But if you have other software, you see here quite some other elements, like Python is very known. We will use OpenMPI, but there are also other tools which might be interesting for other users. Hence, many of these things are also part of normal documentation in these systems. And that's really all I wanted to talk about in the first part of the lecture. In the second part of the lecture, then we will motivate the scheduler and then connect it nicely with something called monitoring on HPC system. If you remember, these were both HPC ecosystem system tools, if you want. So monitoring with Ganglia is quite common, and then using the scheduler like Slurm to really have a batch processing of your job alongside all the different users, to use a compute nodes and to use them in the completely safety manner, because many other users are also using the compute nodes. So we have to have, let's say, a schedule like you have with your university lectures, when is what to be run on the HPC system. And that's what we will talk about in the part 2 here, and we break here for a couple of minutes.